question 3, we have first of all to predict the sign of delta S for that reaction at the top. So again, the thing to focus on is the moles of gas. And you can see we've got 5 moles on the left, 1 plus 4. But because tetrachloromethane is a liquid, we only have 4 moles of gas on the right. So there's a decrease in the moles of gas from 5 to 4. So we predict that delta S should be negative. Because there's a decrease in the moles of gas. And that's all you need by way of explanation. Decrease in the moles of gas. So less disorder. Always bring in that word disorder when you're explaining things to do with entropy. So the next thing then is that we can actually use these numbers to calculate that to see if it's true. So these are molar entropies. So that means that a mole of methane has this much entropy, 186 joules per Kelvin per mole. And these are numbers which can actually be measured, and we don't need to know how you do that, but these numbers are known because they can actually be physically measured. And you can use them to calculate what delta S would be. So the way to think about that is that as this reaction happens, you gain these products. They're formed, and therefore you gain the entropy that they have. So it's going to be plus the entropy of the products formed, but you lose the reactants, and so you lose the entropy that they had, so it'll be minus the entropy of the reactants. So the key thing is you've got to get that the right way around, and if you think of it in those terms, you gain the product, therefore you gain the entropy that the products have. You lose the reactants, therefore you lose their entropy. The way to approach these is to add up the total entropy of the reactants, and then separately add up the total entropy of the products, and then do the subtraction. So we can write down that S naught of the reactants, well, we've got methane, so that's 186, plus 4 lots of Cl2. The crucial thing is to remember that that means 4 moles of that, and it's 233 for 1 mole, so it's 4 times 233, which adds up to 1118 joules per Kelvin per mole. And S naught of the products, so we've got 1 of those, so that's 216, plus 4 lots of HCl, so 4 lots of 187, which comes to 964 joules per Kelvin per mole. So putting those together, we get that delta S is equal to S naught of the products, because we're gaining their entropy, minus S naught of the reactants, because we're losing theirs, is equal to 964 minus 1118, which is minus 154 joules per Kelvin per mole. Is your answer. And you can see that that is indeed negative as we predicted, so the simple idea works, that it does correctly predict the sign of delta S. So you can always use this kind of approach if you're given molar entropies. It's possibly worth noting that you can also see from these numbers that what we're saying about the relative entropies of liquids and gases is a bit simplistic, because you can see that CCl4, which is a liquid, actually has a higher entropy than HCl, for example, which is a gas, and that's because it's a bigger molecule, its energy levels are closer together, and so you can get more dispersal in a big molecule than in a small molecule. But it doesn't matter, because the contribution of moving from a gas phase to a liquid phase nevertheless factors into this and means that you get the overall prediction right. So just don't look too carefully at the numbers and think, oh, this doesn't seem right, because it is more complicated than we're saying it is. but you get the prediction right by saying if there's a decrease in the moles of gas, delta S will be negative. Question 4, first we have to notice this very low entropy of carbon in the form of graphite compared to the others. And again, it's not looking for anything very sophisticated here. It's simply that this is a solid, whereas the others are liquids and gases, and you expect the solid to have the lowest entropy because it has the least disorder. So that's all you need to say. And then it wants an equation for the formation of 1-chlorobutane from its elements. So this is 1-chlorobutane, which is C4H9Cl as a molecular formula. So the equation for formation means that we've got to make 1 mole of that from its elements. So that means we need 4 moles of carbon. We've got 9 hydrogens, so that's 4.5 moles of H2. Remember, it's the elements in their standard states. So hydrogen is H2. And we've got 1 chlorine, so that's half a mole of Cl2 in the gas phase. Gives us 1 mole of C4H9Cl liquid. So that's the equation that it wants. And then it asks us, first of all, without calculating anything, to predict the sign of delta S. So you can see again that we can just do that by noticing that we've got 5 moles of gas altogether on the left, none on the right. So we can say that the moles of gas decrease 5 moles to 0, which means that there's less disorder when the reaction happens, which means that delta S should be negative. Okay, so that would be our confident prediction. And then we can crunch the numbers to see if that's true. So you just use the same approach as before, and you say that S0 for the reactants, and you just add up all those things on the left hand side. So it's 4 times 5.7 for the 4 carbons, plus 4.5 times 130.6, plus half a mole of chlorine, so a half times 233. Okay, so we can work that one out, and then we have S0 of the products, and the product of course is just that, so that one we can just read straight off is 186.3. So this adds up to 722, and so again we can do the subtraction, so make sure you get it the right way around. We're gaining the product, so it's plus that. We're losing the reactants, so it's minus that. So we get that delta S is equal to plus 186.3 for the chlorobutane, minus the entropy of all those reactants, so minus 722 is minus 535.7 is your answer. And remember, the unit of entropy is joules per Kelvin per mole. Don't forget to put units on your answers. So that's the value you should get for delta S. And then, we can just note that that's, as we predicted, very negative, so that fits in with the idea of the decrease in the moles of gas. And then in part E, it says that this number would be completely wrong if we change the temperature from 25 degrees C, which is the normal standard temperature, to 100 degrees C. And it says, why do you think that might be? And the answer to that is going to be that one of the substances may be in a different state when the temperature changes. And obviously if the state changes, the entropy changes a lot, as we've discussed, and therefore that will affect the values of the value of delta S. So if we look at these substances and think, well, what could change when we go from 25 to 100 degrees C? Well, hydrogen and chlorine are already gases. They can't get any more disordered than they are already, so it's not to do with them. Carbon is a solid, so in principle it could, but of course what we know about carbon is it's a giant covalent structure, and they have very, very high melting and boiling points, thousands of degrees C. So nothing's going to happen at 100 degrees C. So it's this one. Okay, this is a liquid at 25 degrees C, but we know that simple molecular substances like that, all you have to break are intermolecular forces, which are relatively weak, to turn them into gases, and that may well happen by the time we reach 100 degrees C. And that would make the entropy of this much higher than it is now. So it would mean that this term would be more positive than it is now, and that would make this less negative than it is now. Still going to be negative, but not by nearly as much. But all you would need to say for answer the question is because the chlorobutane might be a gas at 100 degrees C, therefore its entropy would be higher, and that would change the value of delta S.